Hi, my name is Xu, and I'm honored to be here today to present our recent work, a unified model for continuous conditional video prediction. So first of all, what is conditional video prediction? Basically, given a video clip, we can take some frames at the input of a model, and our target is to predict the missing frames. For example, if the missing frames are the future frames with respect to the inputs, the task is video future frame prediction. Previous work solved different conditional video prediction tasks by different models. So our first motivation is to build a unified model for different tasks because it's more efficient and it's well known that multiple task learning is beneficial for the performance. Besides, video is just some discrete samples of the continuous world. So our second motivation is to build a model which is able to recover the continuous nature and thus make predictions with arbitrary frame rate. In short, our goal of this paper is to develop a model which is able to predict any missing frames with an arbitrary frame rate. Before we talk about the methods, we need to firstly cover two techniques used in our paper. The first one is conditional neural process, or NP. Basically, NP is a type of model which firstly aggregate the paired observations into some compact representation R, and then we predicted the target label conditioning on R. One important feature of NP is permutation invariance, which means that it's perfect for us to unify multiple prediction tasks under the NP framework. The second technique is the implicit neural representation, or INR. INR learns a continuous mapping from input coordinates to target signal values. We can implement INR by several networks or Fourier feature network. Here is our proposed MPVP model. It consists of two parts, a CNN autoencoder and a MP-based predictor. Firstly, the CNN encoder extracts the latent view feature YC from the input context frames VC. At the same time, we use a Fourier feature network to encode context and target spatial temporal coordinates into XC and XT. Then the NP-based predictor generates the view features of target frame Y hat T, and finally we use a CNN decoder to reconstruct the pixel of the target frames. Here is the detailed architecture of the NP-based predictor. We implemented as a transformer with encoder and decoder. So here XC and YC are encoded into some representation MC given this transformer encoder, and then we use a transformer decoder to generate Y hat T given MC, XC, and XT. Here we use a special transformer block from our previous paper, which is called with-HR former block for efficient video feature learning. Neural processes actually needs to learn both the mean and variance of Y hat T, but in practice, we find that learning the variance is expensive and it cannot really capture the motion stochasticity of the video. Therefore, we ignore the variance of Y hat T. Instead, that we use the VAE techniques and we introduce a global latent variable ZE, which is called the event variable, and to take account for the stochasticity, because we assume that both the context and the targets they are generated from the same event latent space. So we use the KO divergence to minimize the distance between these two distributions during the training. So here is our generative process and our final loss function. We firstly test our model for task-specific VFP. The results show that we reach the SOTA on KTH and KT datasets. For cityscapes, we also get the best SSIM. In Figure 3, we show some VFP quality examples on KT and cityscapes datasets. Our model doesn't suffer from the brightness changing problem of previous work MCVD, and in the right we show some video examples for VFP tasks on the KT dataset. Our task-specific model for VFI also outperforms the previous methods with a large margin on different datasets. Here we show some video examples for VFI tasks on SMNIST and KTH dataset. To train a unified model, we need to input random context into the model and make it predict the missing frames. In Figure 5, we plot the metric curves of VFP and VFI of a unified model with respect to different number of context frames. So the performance of the task-specific model are also plotted in this figure, which is denoted by these triangles. So in Figure 5, it validates our observation that multiple task learning is beneficial. And in this Figure 4, we can show that we can predict frames at any given temporal coordinates, even it doesn't exist in the training dataset, for example, 4.25 or 4.5. So here are some video examples for the video pass frame extrapolation and continuous video random frame completion task. In conclusion, we propose the first neural process model for continuous video prediction, which tackles multiple tasks with one model. And our work is the first that successfully adapts the implicit neural representation for a continuous temporal continuous VFP. And we are able to generate video with an arbitrary high frame rate. And finally, our model reaches the SOTA for VFP and VFI on multiple datasets. So thank you very much. If you are interested in our paper, please visit our project page for more video examples and the source code.